Us, can you hear us?
I can hear you.
Great. So, yeah, we're ready. Thank you for coming, and thank you for agreeing of giving us a video lecture. The stage is yours.
Thank you very much. Thank you for organizing. So, I work at the Technical University of Denmark, where I spend as small as possible a fraction of my time to maintain the atomic simulation environment, write code, and make releases. The atomic simulation environment is very much a distributed open source project with contributors from many places, and so everybody contributes a little bit, and but nobody is really. It is not a strongly centralized project. Now, ASE is, according to the relatively recent publication, a software package written in the Python programming language with the aim of setting up, steering, and analyzing atomistic simulations. So, the kind of thing that you can do with ASE, you can set up structures for doing calculations. Then you can read and write a lot of different file formats. Then you can script calculations using a lot of computational codes, often DFT codes, sometimes force fields. Then the special thing about ASE is that instead of writing an input file to do a calculation, you write a Python script. So everything is done in Python with objects and functions and methods, and there is no input file as such. This makes it very flexible. You can write scripts as complicated as you want, which is of course both good and bad. ASE also provides a lot of extra features on top. There is a GUI and there are command line tools, and there is a lot of documentation on the web, so feel free to check out the web page. Also, I should mention it is all free software. It is the GNU LGPL license, which means you can use it for any purpose and modify the code and distribute the changes and so on and so forth. So, since you're going to be doing exercises with ASE, and since most of the work that you will be doing with ASE is in Python, it would be appropriate to have a look at the Python programming language and what that is. So Python is a programming language from, I think, 91. It has a very dynamic, expressive syntax, and you don't need to declare variables. It makes language very useful for scripting. And a good way to get started with Python is, outside of reading the Python documentation and the online tutorials in Python itself, an easy thing to do is to start the interactive interpreter. And the interactive interpreter is basically like a command line. You write some code and it executes the code. And you can see a few examples here how to print. When you're actually developing scripts, it's quite nice that you can play around in the interpreter and try some of the things interactively. Then you can make mistakes and correct things until it works, and then you adapt the script gradually. So also, if you ever need to multiply some numbers or anything like that, don't bother starting one of these inefficient graphical calculator programs. Just start the Python interpreter and do the mathematics there, because it really does everything. So Python has become very popular in different branches of science, often data science, but we have seen over the recent years an immense increase of interest in using Python for also material science. And one of the, aside from the expressive syntax, one of the things which really facilitates scientific work in Python is a so-called Scipy Stack, a collection of Python libraries which includes several efficient ways to work with arrays and provides optimization algorithms and plotting and everything. So there is Numpy. This is a very basic library in a way. It provides this n-dimensional array type. So this array is implemented with a very easy to use indexing syntax. So you can index it and you get an array with fewer dimensions or extract numbers in particular ways. And you can also multiply them and do other basic arithmetic. And the backend is written in C, so it's relatively fast, although it is not as fast as writing your own C code or using BLAS libraries. Then there is Scipy. Scipy goes beyond Numpy and provides many algorithms for optimizations and other things that come in handy. A lot of special functions, for example, and it's all integrated, so it works with Numpy arrays very well. Scipy also provides sparse matrices and a host of other things. Then there is Matplotlib, which is what, from my perspective, completes the package. We often need to generate plots, and Matplotlib does a very good job of that. It generates publication quality plots, basically. Matplotlib also has excellent documentation. There is a huge gallery of examples and a lot of help to be found on the net. There are also other interesting projects in Scipy. There is IPython, which is like the Python console, but with extra features that make it particularly easy to use. There is Sympy, which can do symbolic algebra, and go and have a look yourself if you're interested. It makes life easy. So indeed, I would recommend to everyone to learn scripting and programming to some extent. It is very useful for doing all types of scientific work, and at least when I was writing my PhD back in the days, it was I would always automate every aspect of the generation of papers and reports and the computations themselves. You can really get an efficient workflow that way. So back to ASE. So historically, at DTU Physics, there was density functional theory code called the capo. This was written in Fortran, like many codes, and like many Fortran codes, it became kind of difficult to maintain and use, and everything that had to happen in the capo needed to be implemented in Fortran, and that was difficult because Fortran is not the nicest language to work with. And then Sune Bain and Carsten Jacobsen published this, the original ASE article, an object-oriented scripting interface to a legacy electronic structure code. So in this case, it was an interface to control the capo, but using object-oriented structure, and then it was possible to run different algorithms that were controlled from Python, but were actually computed by the capo. Then things were expanded, and some of the code was not maybe nearly the way it should be. It was then rewritten to become ASE2, and then eventually ASE3. So nowadays we have ASE3.22, so we have had 22 releases of ASE3, and it seems to be doing well. So no more rewrites, I guess. So ASE3 was actually started by Jens Jørgen Mortensen, who has been the lead developer for many years. I eventually took over most of the development around 2007. So although I've been involved longer, it's much of the history is actually before my time. So, but this has a very healthy community, a large number of contributors. You can, if you're interested in the code development, you should go to GitLab. You can also report bugs there. And of course, a shameless plug for our recent reference paper again, which also contains a lot of coding examples. You may want to check that out as well. Okay, so what's it all about then? In ASE, the main purpose of the library is to facilitate scientific computations on atomistic systems. So the central object that one will be seeing the most of would be atoms, which represents a collection of atoms with some chemical symbols and positions. A unit cell, it can also have boundary conditions, periodic boundary conditions or not, and it can be equipped with different physical quantities as well. Then there is a number of modules to help with setting up physical systems of typical use cases. These will typically be factory functions that then return an atoms object in some way. So you can set up molecules. ASE isn't really a chemistry-focused program, but there is this database G2 of small molecules that you can set up any of the standard molecules by just querying that. So water and a lot of small molecules. Then there are several tools to set up crystals working in different ways, some of them general, some of them quick and dirty. Then, since the community has historically had a strong focus on catalysis on surfaces, there are also a lot of surface building tools. Then there is a GUI, support for a lot of file formats, and then there is a calculator interface. So the calculator interface, well, a calculator is a kind of black box which knows how to calculate forces and energies and probably other things. So in order to do calculations, you equip atoms with a calculator, and then you can call certain methods on atoms to extract, to calculate and extract data. Many of the calculators call external DFT codes, which are separate projects that many of them are well established. So some examples of calculators are EMT, GPOR, NWChem, Abinit, and VASP. So EMT is a built-in toy calculator in ASE, which can do simple things. GPOR, I'm going to talk about that later. It is a projector augmented wave code originally started at the geophysics, and then different projects that are truly independent. And there are quite a few calculators by now. I didn't count them exactly, but at one point there were 30. So let's have a closer look at how we actually write things in ASE, and I would like to know, is everything all right with the sound and video and...
Yeah, everything is fine, yes.
I suppose, so nobody complains and the computer seems to be working, like the browser didn't crash or something, so it's probably fine. I'll just go on then.
It's all fine for us, thank you.
As I said, the standard way of using ASE is generally through writing Python scripts. And so in order to set up a structure, you can either call the atoms constructor directly, or you can use some of the factory functions. So a simple example here, we import the atoms class from the ASE module, so standard Python. Then we create our atom subject with an atom of gold. We say it should have periodic boundary conditions in all three directions. And then we provide a cell. So here we provide a cell with the lattice constant of gold. And this is a standard form of the face-centered cubic lattice. So this is a standard face-centered cubic gold that we are setting up. We can print it, and there will be a description in the terminal. And we can call the very useful view function from ASE.visualize. This opens the ASE GUI, and one can hence easily see what was going on in the script and export, render graphics and export to PDF or PNG and things like that. So here we see the cell we just set up, but repeated as a 2 x 2 x 2 supercell. And here below we have an example of importing and using one of the factory functions, where we just ask for a benzene molecule, and that's a simple task. We just need to know the names of these molecules, but they are documented somewhere. For slightly more advanced structure building, there is the crystal module, the space group module. So in this case, typically one encounters published information that specifies materials via an atomic basis and a space group, and the cell parameters, so the lengths and the angles of the unit cell. And so one will typically have this symmetry reduced basis, and what the crystal function does is to look up the symmetry operations of the space group, and then it generates all the symmetry permuted atomic positions so that it generates a real 3D version of this crystal. So we have an atomic basis with 2 atoms in it, but we apply all of the space group 136 symmetry operations, and then there will be more atoms. So this is a standard compact representation, and this crystal method can be used to easily generate atoms objects from that kind of information. Also, there is a very common CIF format, the crystallographic information file, which typically contains information in this form as well. So internally, it would use the same function to generate that. Let's have an actual look at the GUI. So you can run the GUI and then use some of the, then we can have a look at some of the tools in the GUI. And let me actually do that. So this is a GUI. We can use different options here. We don't have any atoms right now, so we can say add atoms, and then we can write the name of a molecule if we know the names. One of them is H2O. So now we have loaded an H2O molecule. And then we can do simple operations like let's say we want this on a surface. Well, I'll just delete it, and then we can try to set up a surface. We can repeat the surface a little bit. Now here we have a gold surface. Let's add a box in the Z direction. So this is our surface. It extends infinitely in the horizontal direction. If we want to add a water molecule to it now, we can do that, and now we have it. And then we can use other features of the GUI to control M, and then we can move it around. We can also rotate it. So I hope you will find the GUI useful. Also, we have the GUI translated in something like 7 languages or so. So if you think it could be fun to translate it into your language, please get in contact. So the other thing that ASE provides, which is not quite Python scripting, is the command line interface. So there are quite a few commands to help with different things. Generally, there is the GUI is one of them. Also, some of these commands are handy for plotting particular things. So let's say that I would like to build a band path for a system. We can use ASE build to set up a crystal, and would generally use the help pages to see the command line options. this one supports some simple simple structures. So it's easy to set up things, the standard faces of elements. So for example, we can do, I think it's -x, diamond, silicon, now we have created and written one of the ASE formats. This we can open in the GUI. But also we can run ASE reciprocal. ASE reciprocal is a handy little utility in case you are into electronic structure. It plots the Brewing zone of the system, and it determines which prevail lattice it has. So you can come along with any system and it will automatically determine, so in this case it was an FCC, and then it knows all of the special point, the high symmetry K-point names and coordinates, and draws as suggested bandpath. So these follow the same conventions as AFlow, which is one of the libraries that, a framework which particularly generates band structures for solids. So many little plotting tools and other utilities can be found here. So the other thing I should mention, there were all these different formats that ASE supports. The ASE info command can be useful to see something about what ASE supports and other installation info. So in case you're installing it, ASE info will list all of the version numbers of different libraries and how the installation is set up basically. And you can also see a long list of all of the formats that ASE actually supports. ASE info.formats. We get the whole thing, and it's a quite long list. So, and of course, if your favorite format isn't there, maybe you should consider contributing a reader or a writer for that format. We can see Espresso input files it can read and write them, but only a single atom subject, and they have the extension .pwi. Those are Espresso files, as an example. So of these, so there are 95 formats right now actually. Of those, there are some formats that are specific to ASE, so they are specifically defined so that they can represent the kind of data on an atom subject. So when you actually work with ASE, you will probably use the trajectory format. That's an efficient binary format. It can store any number of images. You could write trajectories, for example, from a relaxation or molecular dynamics. The trajectory format is actually a special case of the more general Ulm format. It's a general purpose binary format. Then ASE also uses JSON to export data for example, when building structures or band paths or band structures. Typically these objects can be saved to JSON so that they exist as almost human readable data, and you can run these little command line utilities on top or otherwise transfer them around. ASE also offers a database which can work with different backends. So this database is handy if you do a lot of calculations with different parameters. You can connect to a database and write all of the information into that database, and it will be possible to query it efficiently. So for projects that really do a lot of calculations with parameters with complex internal relations, well, the database can be quite handy for that. And the database can also be integrated with tools to visualize its contents in a browser. And some of the I/O formats finally are graphics formats, actually, like PNG, or you can animate the atoms as GIF, or you can use PovRay for really high, really fancy rendering with ray tracing. So the way that you actually read and write atoms objects, well, from ASE.io you can import read and write. That is a standard way. And here we effectively convert a CIF file to a cube file as an example. So let's get to the actual computations. This is how one would write an actual calculation with ASE. So again, we need to import the things that we are going to use. So in this case, we want to run let's say we want to run a structure optimization of water. The first thing that we can do is to set up the actual water. We would specify the chemical symbols and then the positions. So these are handwritten positions. So I just put one of the hydrogen atoms a little bit to the left, the other one a little bit to the right, and the oxygen a little bit further up. So it's a 90-degree geometry. And then we need to center the system in a simulation box if we want to use GPO to calculate it anyway, because GPO always needs a simulation box, but that depends on which code you're using. Then we set the calculator, and we can finally create this optimizer, which then runs on top of the atoms. So the atoms were called system. What we do here is that we create a BFGS optimizer on top of the system, asking it to write to a particular trajectory and to write additional things into this log file. And then we can run it until the maximum force on every atom is smaller than 0.05. So that's how one would write a script. I think yeah, well, one would run the script like this. So I'll just repeat that. So here we have the file. This should be the same. We run it. We'll just take all of the output into some file. And this should be relatively quick. So when creating the GPO calculator, I specified some parameters that will be relatively quick. And we can then see which files appeared during the calculation. There was this opt.log, which tells us how the calculation converged. So in the beginning, the force was quite big. This is in electron volts per angstrom. And then after 5 steps, the force got below the threshold, so the optimization completed. And we can see the energy going down as well. We can also open the trajectory in the ASE GUI. So here we see the energy going down for each iteration. And we can play the actual optimization as a movie. Now if you rotate this, we should see the molecule get the actual geometry that it should have. So it goes from 90 degrees. We can see the angles listed down here when we select three. When we select three atoms with the mouse, it lists the angles here. So in the end, it is close to these 104 degrees. At the beginning, it was 90 degrees. So that was our first calculation. So these basic properties can be computed by calling get potential energy, get forces, get stress, and get dipole moment, and then it delegates that request to the calculator and returns something. And some calculators also have their own methods, so you can get eigenvalues and occupations if you're doing density functional theory, or get information about the k-points, for example. So what actually happens when we perform a calculation is that, as I said, the calling get potential energy, this delegates a request from the atoms to the calculator to get that energy. And then the calculator can do a number of things, and there are different ways in which different calculators work. So most calculators in ASE are file I/O calculators, which means that they generate an input script for an external code, and then they run the code on that script. Then the code solves the Schrödinger equation, or does the Kohn-Sham equations more likely, and then that code probably leaves some output files, which the calculator then reads. And then it can return the number to the atoms, and so that's how it works in the simple case of file I/O. Then there are different kinds of communication as alternative to file I/O. Some codes can run in the background and receive multiple sets of positions, and then it's possible to run an algorithm where you only need to start that program once, whereas in the simple file I/O case, you need to start the program many times. In the case of GPAW or things that are written directly in Python, it directly links to a library or imports it in Python, so it all works inside one process, not multiple processes. So that makes some things simple. It's easy to do advanced things, but the implementation can be complicated. Maybe you need a parallel Python interpreter. But it grants a lot of flexibility that you can use a calculator as a Python library. Most of the codes either work using file I/O. So every time we run it, it needs to start the program. And then the program runs entirely, as I said before. And then after that, it needs to leave some files, but the program ends. So the next time, let's say that we are doing an optimization, then the atoms will move around, but we need to do a completely new calculation next time. So this could be more efficient because most DFT codes would benefit from reusing the wave functions from one step in the next step. And so now one of the big, slightly more recent things in ASE is the socket I/O calculator, which everybody should consider using whenever possible. So there is this code called IPy, which is specializes in molecular dynamics, with first principles codes. And they have defined a protocol based on sockets, and ASE then implements this protocol and provides a socket IO calculator class such that you can communicate with any of the codes implementing that protocol. The way that it works, when you create a socket IO calculator, ASE starts a kind of server, and then also a client as a separate process. And the client then connects to the server, and then they can talk over this socket connection. And then the server can send atomic coordinates and unit cell, which are typically the things changing in simulations. And the client will then perform the calculation. Maybe the client runs in parallel. Then it will calculate these things and return them over the socket to the server. So the server probably runs in serial, which also keeps the script simple. So this works with several calculators. There is Abinit, DFT, B+, Espresso, FPGA Ames, NWChem, and Siesta. And there are even more codes that can support this protocol. And ASE can also work with those, but it's not nearly as easy because there is no automatic process to set it all up. Then one has to manually launch the server and the client. Anyway, who actually use the socket IO calculator to write an optimization. The script looks like an ordinary optimization. In this case, I have put an example with NWChem. So again, we create a calculator. We need to set up the atoms, and then we need to create a calculator. That's normal. But then we need to specify some specific arguments to tell it how to communicate. So in this case, we use a Unix socket. This can also work over internet sockets. So it's actually possible to run this across a remote system as well. You can control from a desktop computer or laptop things that go on a supercomputer this way with the INET protocol. Anyways, then we set up an optimizer as normal, and then we use this special construct with, which tells Python to remember to please close the socket and the processes nicely when it's done. And then, so this is where the actual communication and number crunching happens. And then one is free to write other things in this loop as well. One needs not only run optimizations or dynamics. One could do any of quite a few things. So as it turns out, ASE has a lot of algorithms that can run on top of calculators that provide energies and forces. So there are the typical gradient-based structure optimizations, and also it's possible to attach constraints to atoms, which means that you can very flexibly express. Well, it's possible to fix atoms, and it's possible to fix some degrees of freedom, or there is even a constraint which can take an arbitrary matrix that reduces the number of degrees of freedom according to a kind of linear operation. So this is very flexible, and of course the really big advantage is that if you can use these constraints with ASE and the socket protocol, then it really grants a lot of flexibility to work with all of these codes that it supports. So all of these codes don't need to implement those constraints. So there are also some algorithms for doing global optimizations, minima hopping and Bayesian hopping. There is a genetic algorithm. All of it you can find on the web page. and there are quite a few different kinds of molecular dynamics with constant temperature, pressure, and other controls. There are algorithms for saddle point searches and for doing vibrational analysis. Here we have one representation of the relationships between these objects. So in the bottom we have the calculator interface, which is supposed to be a black box. So there are different implementations of that. And these algorithms don't generally talk directly to the calculator. Instead, they talk to the atoms. And the atoms may or may not talk to constraints. So when you move the atoms around, well, the constraint will detect it and enforce whatever they're supposed to enforce. And then it kind of transparently they act transparently as a layer under the algorithm which is actually running. So the algorithm which is actually running could be any of the things here. Some of these are optimizers and dynamics. Then there is also a nudged elastic band algorithm for determining reaction paths. And there are more. So again, you may want to have a look at the publication or the web page to get a more complete overview of the actual features. Now, I would like to say a few things about GPOR as well. The example that I showed was with GPOR, and GPOR is an electronic structure code using the projector augmented wave method. The special thing about GPOR is that it is written in a combination of Python and C. So as I said, there are many advantages of using Python, but Python itself is not really a number crunching language. So the combination of Python with C allows some parts of the code to be written in C where it runs very efficiently, and other parts to be written in Python. You can find the web page. So one of the main advantages of GPOR is that it's very well integrated with ASE. In fact, historically, GPOR has been one of the driving forces for the things that are implemented in ASE because of the significant number of ASE developers that are also using GPOR. And then we try to generalize as many of these features so they work with as many calculators as possible. So GPOR actually has three different calculation modes. One of them uses finite differences in real space grids. Another uses linear combination of atomic orbitals. And the third one uses plane waves, which has been very popular lately. Plane waves have a lot of advantages. So since it is so nice to write things in Python, it also becomes easier to do complex things such as parallelization. So one of the strong points of GPOR is that the parallelization can be used there are many combinations of parallelizations that can be used at the same time to achieve maximum scalability. So you can in finite difference mode you can parallelize over k points, and you can parallelize over domains, and you can parallelize over bands, and so electronic states at the same time. I think GPOR was maybe the first major code to have all this parallelization implemented. And in LCIO mode, for example, there has also been a significant focus on the parallelization. So a lot of the steps that involve only the density, for example, they can run quite quickly because it can redistribute the density from one grid to another on the fly, and then do the number crunching and then distribute it back. And this trick is used in a lot of places where there would otherwise be bottlenecks or things would not be so efficient. For example, because of load imbalance, when one process has more data in front of it than another to work on, then there are a lot of these distribute, calculate, redistribute tricks in GPaw. So a lot of people think it's strange to write a DFT code in Python. So just to properly comment on that, there is a common case in computing that by far the most time is spent in a tiny proportion of the actual code. And so Python, being generally speaking an interpreted language with a lot of dynamic typing and everything is an object that is allocated on the heap and other things that are nice, well, that's not very fast. So a lot of things become very slow if they're written in pure Python, and Numpy only solves part of that problem. Numpy still does not really allow writing tight loops or otherwise do fully efficient number crunching. So so hence in GPaw the combination is between Python and C. So we get most of the benefit from Python by writing 90% of it in C, and only a little bit is written in the horrible low-level language, in this case C. This is a huge advantage because all of the other DFT codes that are written probably in Fortran, well, they have to implement everything in Fortran. So all of the gluing together of components, for example, the SCF loop, these are complex things, but they don't need to be efficient. Only the individual operations inside need to be efficient, but the actual loop, the actual structure surrounding those doesn't need to be efficient. Also, reading and writing files is much easier in Python, and particularly string processing if you want to print something. And Fortran is like really an ancient language, and it tells when due to all of the static memory allocation and other things for even basic string operations. Then also there is a depressingly large number of parsers for pseudo-potentials written in Fortran most likely, and all of this you can really speed up by writing those things in Python. And as I said, also the parallelism, which is so advanced in GPaw. It's easy and fast to implement those things. So even if the code itself does not run so fast, the fact that we can at all implement and maintain a code base with all of these parallel tricks, that really demonstrates the advantage that Python provides for computation. And so there are a few actual disadvantages as well. There is an interfacing layer between Python and C, which is not beautiful. And also debugging tools and performance measuring tools tend to not work as well together with Python. some of the static analysis, some of the dynamic analysis codes like Valgrind and other tools that are typically used on compiled binaries, they will have a hard time outputting legible information when they run on GPOR. So it's a trade-off in the end. So if you want a nicely scriptable code, you should check out GPOR. There are the 3 different modes that have each their trade-off. So the real space grids are quite accurate and can parallelize very well, but then the grids are not an enormously accurate representation compared to plane waves, because you need a rather fine grid. Otherwise, you get this little so-called egg box effect, where the grid makes space slightly non-uniform, and this introduces some forces or unphysical effects. Then there are the numerical atomic orbitals, the LCIO mode. That's very fast because you have relatively few degrees of freedom. So on a modest system, you can do thousands of atoms. However, the limited size of the basis makes it not nearly as accurate, and you cannot just add more functions because you need to choose those functions relatively intelligently, and this is not such a simple task, at least not if you care about performance. And then there is the plane wave mode, which is extremely fast for crystals and small systems. And plane waves are really well behaved numerically, so in the end it is now the most popular mode, even though it's the most recent one. At least in the GPOR implementation, it is not yet as scalable as the real space grid method. Some things don't utilize all of the parallelization degrees of freedom, and of course plane waves are also delocalized. They overlap with all of space. So localized functions are no longer localized, or at least not in the same way. If you start working with ASE, then you should get in touch with the community. So there are plenty of places to get help. There is a mailing list. There is a chat on Matrix, which has become very popular recently. And there is a forum on matsci.org, the Unified Materials forum. So that has forums for a lot of different codes, and well, ASE is one of them. So here you have basically the information, and if you are interested in developing the code or in reporting bugs, then you should go to GitLab, and there is a lot of activity there. So soon we should get started on the exercises. So there were some questions of whether the exercise computers were quite set up to run with GPOR. It turns out that it does not work right now. So, but I think we can use VASP. Nevertheless, we should probably clear that up before we get too far. Anyway, you can find the exercises at this link. So just go to the ASE webpage and click around, or just just type this if you're fast enough. And basically, it should be possible to do the exercises with VASP. But if there is some problem, we may have to resort to this toy calculator EMT, which then is a little bit unphysical for some systems. The EMT calculator actually works with, it's a force field for FCC metals, but it's very useful to have for debugging. So it also works with some molecules, but the results are garbage, not unphysical. So don't use it for something serious. I think, so in principle I still have some time, but I'm not completely sure about the format of the exercises actually.
Hi Ask, thank you for your talk. Maybe we could start with questions if there are some questions from the audience. And as far as I'm informed, the exercises should start at 11 after the break. Yeah. Okay, do we have any questions to the ASE code? Yeah, please. If anybody has questions, please come down so that Ask can hear you. Can you come down to the laptop?
Hello, thanks for the talk. Just a quick question. Could you say something about the relationship with AIDA framework?
So the AIDA framework is focused on high throughput workflows and data provenance. It is a somewhat higher level of controlling things than ASE. ASE itself is mostly just a scripting framework, so you choose what to do, but you are also responsible for how you handle your data. So they do different things, but of course AIDA also provides many of the same things, the actual ability to do calculations. So actually there is I would like to mention that there is another related project, ASR, the Atomic Simulation Recipes, which are being developed at DTU Physics. So that's also a kind of extension for ASE to facilitate high throughput computations. And the idea is to reach the rather large selection of calculators that ASE can offer and enable a long list of different tasks like band structures and PDOS and so on and so forth, leveraging all of the infrastructure already in ASE. So this is not quite AIDA, but it is an alternative which is more closely related to ASE.
Okay, thank you. I think we have another question too.
Hi. I have a question about the GPAL, about the LCAA mode. So you said the numerical basis functions. Can you say a little bit more about it? What type and when they are good and when they're not so good, and so on?
It's closely related to Siesta. So this was actually my master project many years ago. We wanted a special mode for GPAL which could use localized basis sets, particularly because that would make it easy to do Green's function-based transport, but also because the localized functions are fast, since there are not too many of them. So, as I said, it's much like Siesta. These are numerical atomic orbitals. So what a basis set is generated by first having a PAW setup and then in a spherical system, solving for the wave functions of one atom in that radial system where the PAW setup is defined. And so with those basis functions, you can define different extensions. So you have the physical basis functions that are actually the states on the atom, and then you can define some extra ones, and the methods for that are basically equivalent to those in Siesta, not quite, but mostly. And so the result is that you get some basis sets where the standard double theta polarized is quite useful, but it's very useful for doing a large number of calculations where you don't care so much about the accuracy. So if your project is to analyze a particular chemical reactions and get exactly the energy barrier, then maybe it's not quite accurate enough. But it has many other applications. It's very good at getting trends, and also most of the work done in a project, like optimizations and things like that, can be done in LCIO without great loss of accuracy. Also, for LCIO, there is a GDGFT time propagation implementation, which scales to quite large systems as well, as a relatively recent development.
Okay, thank you very much. Helpful.
Do we have some other questions? Yeah, please come over.
Ask just a question. Typically, the workflow, how it is when you have a cluster where you have certainly some queuing system. How do you submit then the parallel jobs? And does then the ASE, I think in the background it starts with MPI run. It runs the given software. Does this MPI run then realize that he's under queuing system environment and knows which are the hosts and host files and all these things? I suppose you tested it more than me, so I wanted to ask.
Right. So usually, so nowadays most clusters use Slurm. So in that case, you usually end up writing srun something, and so in the case of gpaw, you generally use a gpaw command to launch a parallel process. So it's something like gpaw-p and then the number of processes and then the script. And you can write srun in front of that, and then it will run in parallel. So in the sbatch script, you would just modify the typically final line that contains srun. If you have MPI for Pi installed, then you don't need the gpaw command. Then you can just launch it directly using the Python interpreter. This can be useful for some ASE calculators that can run in parallel but are not gpaw.
Thank you. Anybody else? I will also have some questions. So my question is, does ASE support some kind of embedding so that you can use two calculators to different codes to calculate a part of the system and then another calculator which calculates another part of it?
There is a QMMM feature. Now, I haven't personally worked on it. I have done some code review, but it's not quite enough that I can say much about the capabilities. But it basically allows doing QMMM, combining a force field code with an electronic structure code. There must be some documentation online, but I wouldn't be able to produce an example myself.
Okay, thank you.
Can I comment on that?
Yeah.
So, closer. So That's one of the exercises here. We have two codes. So we have a SPR KKR code and MS spec, which is a spectroscopy code, and the ASE is used to combine them as well. So we will have some exercises on that. So first you do the self-consistent calculations with the SPR KKR, and then you go automatically to the MS spec and calculate photoelectron diffraction or something. So you can combine them.
But it's a sequential usage. It's not,
That's a
they're not
kind of
working
sequential,
and
yeah,
exchanging data. Okay.
Well, they are exchanging data. They're exchanging, in that case, you saw always in multiple scattering is the potential, which is the main quantity we exchange. So we do the self-consistency with SPR KKR and exchange then the potential, and all is done on the ASE, under ASE framework. So we have some examples, so we will see that later on.
Great. Thank you, both of you. No other questions? Then I have still one question. You said it's not much focused on chemistry, but are there ways of getting arbitrary molecules constructed in ASE, such as an import from a SMILES string, or importing from the PDB database or materials project directly by getting a call or parsing?
There is no SMILES parser. This would be a nice addition because it's a kind of it's a nice handy feature, but it would need some kind of algorithm to actually construct the positions in real space, which is not nearly as easy. So implementing one would be quite a bit of work. It's possible to read PDB files and probably write them. So PDB, I think, has this connectivity, and I cannot remember the extent to which this is actually supported. Since ASE tends to be a little bit focused on DFT codes, there are no connectivities then. But some kind of extension of ASE in the direction of representing connectivities and topologies, well, that would be a very useful addition, in my opinion. Sometimes some functionality pops up which goes in that direction, but it tends to be too specialized to be truly a uniform API. Also, it's possible to get molecules from PubChem. There is an automatic search feature there. I'm not aware of other chemistry-related such shortcuts.
I see. Thank you very much. I think we don't have any other questions currently. So in that case, let's thank our speaker. And I guess we'll have a break now and we'll reconvene at 11. Thank you, Ask.
Thank you very much.
Something in the discussion. So
Oh, sorry, I didn't see that.
there's something in the discussion.
Ask, could you please send us the slides?
Sure.
If there is no problem for you, because we would like to share them with all participants of this call.
Yeah.